showing your computer a photo of a chair, and instead of giving you a blurry blob, it builds the chair in full 3D, piece by piece. That's what PartCrafter does. It's a new AI model that doesn't just guess the overall shape. It breaks the object down into meaningful parts like legs, backrest, and seat, and generates each part in 3D, all from a single image. Most 3D models work top-down. They make the whole shape first, then try to slice it into parts. This one flips the script. It starts with parts guided by a clever compositional latent space and a local global attention system that helps it see the details and the big picture at the same time. No need for pre-labeled parts or segmentation tools. Just one image in, a structured 3D model out. It's like building IKEA furniture minus the manual.
All right, let's dive into the exciting world of PartCrafter. This is a breakthrough in 3D model creation. Imagine it as a magic tool that can take just one picture and generate multiple 3D parts that fit together seamlessly. What's special here is that it doesn't need pre-segmented images. Most systems either build a single shape or do a two-step process, like cutting up the image first and then crafting pieces. PartCrafter's genius lies in two key innovations. First up, it uses something called a compositional latent space. Think of it as a toolkit where each part of your 3D model has its own little packet of information so they don't get mixed up. This helps in making detailed and distinct parts. Next, there's a clever attention mechanism. It's like a well-coordinated dance, making sure all the parts communicate smoothly, keeping the big picture coherent while maintaining the details. They've curated a new dataset with part-level supervision from large-scale 3D object datasets. Experiments show PartCrafter isn't just a neat idea, it performs well, even generating parts that aren't visible in the initial image. It's like having a superpower for understanding and creating complex 3D scenes. They also mention releasing the code and training data, which is great for anyone wanting to explore this tech. Now let's explore the significance of structured 3D models. These models break objects down into parts, like having a set of building blocks that you can mix and match for various tasks. Traditional neural networks often struggle with this because they're not designed to handle such structured components. In 3D generation, diffusion-based models have emerged as powerful tools for creating entire 3D shapes from scratch or images. However, they typically focus on whole objects without diving into part-level details, which limits their use in tasks like texture mapping and animation. Some recent efforts tried segmenting images into parts first, but that method has its own challenges, like segmentation errors and increased computation. Enter PartCrafter, a groundbreaking model that tackles these challenges head-on. It generates 3D scenes with part-level detail from a single image using a compositional latent space. This means it can create multiple distinct 3D parts simultaneously, each with its own set of latent variables. Built on a pre-trained 3D object diffusion model, it restructures these models to work with sets of latent tokens, ensuring smooth information flow both within and across parts. A new dataset with part-level annotations was constructed for training, using assets from existing 3D object repositories. PartCrafter has been tested against other methods and shown to deliver higher quality outputs. Its compositional structure enhances the quality and fidelity of generated 3D models, setting a new standard for 3D syntheses. Now let's delve into the related work on 3D object generation. Historically, various methods like voxels and neural radiance fields have been used. These approaches are known for their compatibility with real-world 3D pipelines. There's a distinction here. Some methods predict shapes piece by piece, while others use latent diffusion, effective with large datasets. PartCrafter stands out because it builds on these advanced methods. Traditional models tend to treat 3D objects as single entities, missing the detailed decomposition artists achieve manually. PartCrafter focuses on part-level generation, a complex area that's been around for ages. Some work has been done on assembling parts by adjusting positions, but PartCrafter simplifies the process. When creating 3D scenes, older methods often required segmenting the input first, which could be cumbersome. PartCrafter eliminates this need, working directly from image prompts without additional segmentation. This makes it more efficient. Moving on. PartCrafter is described as a compositional 3D diffusion model. It generates structured 3D assets by refining several part-specific latent token sets simultaneously. This model takes a single image and a user-defined number of parts to create a detailed 3D asset. By leveraging pre-trained models and a compositional architecture, PartCrafter brings a fresh approach to 3D scene generation. Let's dive into PartCrafter's architecture. Check out Figure 2 as your visual guide. It maps out how PartCrafter processes images to create 3D models. Imagine starting with an input image. It's run through an encoder that breaks it down into smaller pieces, or patches. These patches connect with noise latents, which are like random elements helping create diverse outputs. Here's where PartCrafter's attention mechanism works its magic. By balancing local and global focus, it ensures each 3D model part is detailed and fits into the whole. The underlying tech is based on a diffusion transformer model, known for generating high-quality 3D objects. PartCrafter builds on a model called Tripos-G, which first encodes 3D shapes into latent vectors using a VAE. This method keeps shapes geometrically consistent. The real innovation lies in the compositional latent space. Each 3D object part is represented by its own set of latent tokens. They use unique identifiers to distinguish parts, keeping every piece distinct while part of a unified whole. This approach captures fine details without losing the big picture. Finally, PartCrafter uses a local global denoising transformer. This feature processes each part individually before integrating them, ensuring the final model is intricate and harmonious. It's like fine-tuning an orchestra, where each instrument plays its part perfectly, contributing to a beautiful symphony. Let's dive into the dataset and training setup for PartCrafter. Look at Figure 3 for a snapshot of the dataset structure. You'll see a pie chart and bar chart illustrating the distribution of parts within 3D objects, highlighting how these datasets are rich in detailed part annotations. Now let's talk about the model's attention mechanism. PartCrafter uses tokens to manage interactions across different parts, capturing both fine-grained details and the broader 3D context. Imagine it as a manager coordinating both local and global perspectives to ensure everything works in harmony. This hierarchical attention structure ensures smooth and cohesive information exchange. The training process focuses on refining the details. PartCrafter uses a method called rectified flow matching. It's like fine-tuning the model to predict how parts move and interact over time, ensuring consistent and smooth trajectories. This involves training the model to predict a velocity term based on a noisy latent representation, maintaining consistent motion across parts. Finally, dataset curation is crucial. The team combined various sources to create a comprehensive dataset with around 130,000 3D objects, each potentially containing multiple parts. This ensures the model gets plenty of rich, diverse data to learn from, leading to more accurate and meaningful 3D generation. Let's explore the implementation details of PartCrafter. The team tweaked existing models by integrating a new attention mechanism, alternating between global and local focus. Think of it as switching between a wide angle and a zoom lens to capture both the big picture and the fine details. They trained PartCrafter on powerful GPUs, fine-tuning it to handle up to 8 parts for objects and up to 16 for scenes, ensuring the model was versatile and robust. Now, on to experiments. The researchers wanted to see how PartCrafter stacks up against other models in generating 3D parts that aren't visible in the original image. They were also curious about how using different numbers of parts affects the results. It's like testing a new recipe to see how it holds up under various conditions. For baselines, PartCrafter is pioneering in generating 3D part-level meshes from a single image, unlike some methods focused on fields or not directly comparable ones. They compared it with HoloPart, a method that segments a mesh, and found that PartCrafter excels in generating parts with both high fidelity and independence. This means the pieces fit well together while also standing strong on their own. In evaluation, they used metrics like the chamfer distance and F-score to gauge how closely the generated meshes match the ground truth. PartCrafter showed impressive performance, especially in generating parts that are distinct yet cohesive, proving its capability in structured 3D generation. Now let's dive into the evaluation results. Check out tables 1 and 2 to see how PartCrafter performs in generating 3D objects and scenes. They use metrics like chamfer distance and F-score, where lower chamfer distance and higher F-score mean better performance. PartCrafter consistently outperforms other models like Tripos-G and HoloPart across multiple datasets, generating more accurate and cohesive 3D models. And it does all this faster. In the realm of 3D scene generation, PartCrafter proves its mettle using the 3D front dataset. It surpasses MIDI, another model that relies heavily on ground truth segmentation masks. A step PartCrafter elegantly sidesteps. This means PartCrafter can handle complex scenes without intricate pre-segmented inputs, making it robust for generating high-quality 3D representations. Now on to the ablation studies, which are like peeling back layers to see which parts of the model are doing the heavy lifting. They experiment with removing either local or global attention to see what happens. Turns out, both are crucial. Without them, the model struggles to produce meaningful 3D meshes, highlighting the importance of this dual attention strategy in maintaining structural integrity and capturing complex relationships within 3D data. Let's explore the visuals and insights here. Look at figures 4 and 5 to see PartCrafter's results compared to other methods. Figure 4 focuses on 3D part-level object generation. You can see how PartCrafter delivers more detailed and coherent parts than HoloPart. Different colors highlight each part's identity, showing how well the model segments and structures objects. Figure 5 moves into 3D scene generation, comparing PartCrafter with MIDI. PartCrafter shines by accurately capturing the structure and layout of complete scenes, again using colors to distinguish different objects. This visualization underscores its ability to handle complex arrangements without losing coherence. Now let's talk about part identity control. When identity embeddings are removed, the model struggles to differentiate parts, leading to a collapse. By incorporating control signals into local-global attention, PartCrafter balances mesh fidelity and geometry independence. This is crucial for maintaining both detail and distinctiveness. Finally, the order of local-global attention is explored. With a U-net-like architecture, PartCrafter tests different configurations for placing attention modules. The alternating pattern proves most effective, providing a harmonious balance between local detail and global structure, ensuring robust 3D generation. Now let's understand what makes PartCrafter tick through an ablation study shown in Table 3. It examines different configurations of attention mechanisms and part embeddings to see how each affects performance. The results show that using an alternating pattern for global attention, combined with both local and global cross-attention, provides the best balance of metrics like chamfer distance and F-score. This setup enables effective information exchange and integration across both local and global levels. Figure 6 illustrates how PartCrafter handles different numbers of parts in its output. Whether it's 1 part or 8, the model maintains quality, showcasing its flexibility and robustness in producing detailed parts from a single image. This adaptability makes PartCrafter a powerful tool for various applications. In the conclusion, the paper highlights PartCrafter as a novel approach to 3D mesh generation, capable of reconstructing parts and scenes without relying on pre-segmentation. Despite being trained on a relatively small dataset, it shows promising results. The authors suggest scaling up training with larger datasets in the future and emphasize the broader impact of advancing 3D structural understanding for commercial and environmental applications. Thanks for joining us today. Happy exploring together.